physical and chemical agents for microbial control. Okay. So controlling microorganisms. So controlling exposure to potentially harmful microbes is essential to our lives, right? It's a concern. It's also in the past. We have to be able to control what microbes are exposed to and how they can affect us. So early protection laid the foundation for the control methods we use today. Like burning wood releases formaldehyde, which is toxic to us. Herbs, perfume, vinegar contains mild antimicrobial substances, which helps break down or protects us from these microbes. All right, this is what we used in the past. These are the docs used to wear, very effective masks that we used to wear. All right, so physical, chemical, mechanical methods to destroy or reduce undesirable microbes in a given area. Decontamination. The primary targets are microorganisms that cause infection or spoilage of food. Vegetative bacterial cells and endospores. Endospores are microorganisms that basically dehydrate, form a crust over them, and they go into hibernation. Remember, they're very hard to kill. Fungal hyphae and spores, yeast, protozoan, worms, viruses, prions. All those we can control. Physical agents, we can heat it. Heat, dry, incineration, sterilization, dry oven, sterilization, or you can do moist. Steam under pressure can be sterilization, boiling water, hot water, pasteurization, disinfection. There are all different ways we control microbes. Radiation, ionizing radiation, X-ray, cathode, gamma radiation, sterilization, non-ionizing radiation like UV radiation, and then UV for disinfection. So mechanical removal methods. How do we remove the microbe? First of all, filtration, we filter it out. We can filter air, disinfection. We can filter liquids, sterilization. Okay. Chemical agents, gases, sterilization, and disinfection. Liquids, animate and inanimate. Animate, we use antisepsis. Inanimate is disinfection and sterilization. So disinfection is the destruction of vegetative pathogens, but not bacterial endospores. So if we disinfect, we kill the microbe, we do not kill the endospores. Okay, used on like desktops, cabinets, things like that. Sterilization, complete removal of all destruction of all viable microorganisms. This kills the endospores. Okay, so disinfection cleans, but does not, or gets rid of the microorganism, but not the endospores. Endospores are the toughest thing to get rid of. That's why every dental office, every medical office that uses equipment has to sterilize their stuff with a sterilizer. And we have to turn in a test in the state of California once a week. We have to run a little strip that has endospores in it. We put it in the sterilizer, we send it in to be analyzed. It's all sealed, so you can't modify anything. And they have to make sure the endospores are being killed by your sterilizer, make sure it's working. You get that checked every week. Okay, that's sterilization, killing the endospores with this. Antisepsis, chemical applied to body surface or destroy inhibited vegetative pathogens. It kills the microcorrosives on your skin. The highest resistance are prions, bacterial endospores. Those are highest ones you talked about. Those don't die easily. Those take a lot of heat, a lot of pressure. Moderate resistance, protozoan, naked viruses, bacteria with no endospores, resistant walls, other gram-negative bacteria, and most heat and chemical resistant bacteria like Staphylococcus and mycobacteria. Those have moderate resistance. The least resistance is bacterial vegetative cells, like what gets on your skin, stuff like that. Fungal spores and hyphae, yeast, enveloped viruses, protozoan trophozoites. Okay, those are all easy to kill relatively. So heat kills endospores at 120 degrees, kills vegetative forms at 80 degrees. Relative resistance is 1.5 times that. Radiation, what it takes to kill endospores, sterilization gases, and sporicidal liquids. Okay. Different times, different rates what it takes. To kill endospores is 3 hours with our sporicidal liquids, 10 minutes for the vegetative forms on your skin. This is an endospore. Here's the cell, and it's encased in this thick coating, like kind of hibernates on this thick coating. So sterilization destroys all viable microbes, including endospores. Microbial agents like germicides. Antimicrobial agents are destroy certain microorganisms, like aimed at bactericides, fungicides, virucides, and sporadicide. So disinfection uses a physical process of chemical agent to disinfect, destroy vegetative pathogens, but not bacterial endospores. Important point. Disinfection does not kill endospores. Sterilization does. Antisepsis is actually chemical agents like antiseptics directed to exposed body surfaces, like wounds, surgical incisions, inhibit vegetative pathogens, what you pour on an open wound or cut to help clean it. Agents that cause microstasis. Okay. Antimicrobial agents aimed at temporarily preventing microbes from multiplying. Okay. Methods that reduce the number of microorganisms. Sanitation, any cleansing technique that removes microorganisms from the inanimate surface to reduce the potential for infection or spoilage. Degermination, reduction of the microbial load from living tissue by mechanical means, by cleaning it out and scrubbing it. So here's your list we just went over: decontamination, sepsis, asepsis, antiseptic, disinfectant, sanitation, degermination, and sterilization. Okay, and this gives you all the definitions of what those mean. Just what we went over. And then an example of each one. Okay. So microbial death, they're hard to detect microbes, often reveal no conspicuous vital signs to begin with. So how do you know that you killed them? You have permanent loss of reproductive capability, even under optimum growth conditions. That's how you know they're dead. They're not going to replicate. Okay. Factors that affect it are the number of microbes, the nature of microbes in the population, temperature and pH, concentration or dosage of the agents used to act against them, the mode of action, how it does it, and the presence of other solvents, organic materials, or inhibitors. Okay. So factors that affect death rate. So this is the number of cells. As the number of cells decrease, and sterilization. Again, spores decrease, vegetative cells decrease at a faster rate. Okay. This is sterilization, different times it takes, depending how high the pressure is on it. Okay. So does the application require sterilization? Do you have to sterilize something? Not always. You don't have to sterilize your countertops and things like that. But if you're going to use an instrument in somebody's mouth or in terms of it, they better be sterilized. Is the instrument going to be reused or be thrown away? If it's going to be a one-use thing, don't sterilize it. All right? We don't sterilize dental needles. We use it on one patient, throw it away. It's a one-time deal. You don't sterilize it. There's no reason to. Can the item withstand sterilization, the heat, the pressure, radiation, or different chemicals? Is the method suitable for what you're sterilizing? Will the agent penetrate to the extent necessary to kill it? Is it cost effective? Can you afford to do it? Okay. What we're targeting is the cell membrane, and in bacteria, the cell wall. Remember, human cells don't have a cell wall, bacteria do. So the cell wall becomes fragile and the cell lysis, which means it explodes with some antibacterials. And the cell membrane, we lose the integrity of the cell membrane. With surfactants, we break up the integrity of the cell membrane and the contents leak in or out. So these are surfactant molecules. They bind to the surface of the membrane and they cause an opening in this membrane. And then the cytoplasm things can leak in and the cytoplasm can leak out, basically destroying the cell. Okay. So cellular targets are physical and chemical agents. So protein and nucleic acid synthesis, prevention of replication, transcription, or translation, peptide bond formation, protein synthesis, all those will cause a cell to die. If you stop it from replicating, if you stop it from taking its DNA to RNA, you take it from RNA going to the proteins, if you stop from the proteins going to the peptide bond forming proteins, or from completing it to protein synthesis, basically you stop the cell from functioning. And you can stop with chloromphenicols, ultraviolet radiation, formaldehyde, all that do it. Protein function, disrupt or denature the proteins, like alcohols, phenols, acids, heat, those all disrupt or denature a protein. It becomes useless. So here's your protein, your substrate, your enzyme, and all that. Heat or pH change, it's strained out, it's not functional. The shapes are gone. Okay. Heavy metal bonds to it, they can block the active site. Again, non-functional. So heat or pH change, either higher or lower, or heavy metals, lead poisoning, heavy metal poisoning, gold poisoning, like that. can cause that. If you wipe your hands with an antimicrobial cleaner, you are accomplishing what? Sterilization, disinfectants, antisepsis, sanitation. Okay? You're using an antimicrobial cleaner. You are not sterilizing yourself. Okay? You're creating antisepsis. Okay? That's when you wash your hands with an antimicrobial cleaner. The vast majority of microbes are readily controlled by abrupt changes in their environment. Okay. Some physical methods are heat, cold, desiccation, drying it out, radiation, or filtration. Those ones we talked about already before. So moist heat, lower temperatures, shorter exposure times, coagulation of the denatured proteins, halts cellular metabolism. Dry heat, to moderate high temperatures, dehydration, alters the protein structures, or incineration, burning them. Okay. So moist heat at 121 degrees, it takes 15 minutes to sterilize. At 134 degrees, it only takes 3 minutes to sterilize. Dry heat at 121 degrees, takes 600 minutes to sterilize. At 170 degrees, it takes 60 minutes to sterilize. So you have a dry heat sterilizer. You're not going to be in the hospital running for 600 minutes. That's not cost effective. You get to 170 degrees and run it for 60 minutes. Okay. Thermal death measurements. Bacterial endospores are the most resistant we talked about. Remember, it's endospores are resistant. Okay. So thermal death time is the shortest length of time required to kill all test microbes at a certain temperature. Thermal death point is the lowest temperature that is required to kill all microbes in a sample in 10 minutes. So the two definitions you need to know: thermal death time, shortest time, and thermal death point, which is the lowest temperature, in 10 minutes. So sterilization with steam under pressure. That's what most offices use. That we use at my office. That's an autoclave, 15 psi, 120 degrees centigrade, 10 to 40 minutes. Pressure increases the steam temperature. So as you increase the pressure, you increase the temperature. Steam must reach the surface of the item being sterilized. The item must not be heat or moisture sensitive. If you put something that's going to melt in an autoclave, it's going to melt and be unaffected. I mean, the item has to be heat or moisture, cannot be heat or moisture sensitive. It denaturizes the proteins, destructs the membranes, and it destructs the DNA. This is an autoclave. How it works: it heats it up, puts it under tremendous pressure. You put in moisture and heat, increase the pressure, which increases the heat, let it run. It destroys all pathogens. A non-pressurized station is a tyndallization, which is intermittent sterilization for substances that cannot withstand autoclaving, things that cannot withstand that kind of pressure. Items are exposed to a free-flowing stream for 30 to 60 minutes, and they're incubated for 23 to 24 hours. So it's going to take a long time. Okay? And then they subject them to steam again and repeat the cycle for 3 days. So 24 hours for 3 days, you're doing that cycle. And that's sterilized from that. Used for some canned foods and laboratory media. Okay? Not used in medical offices, it's just not practical. It takes them for 3 days to sterilize them. Boiling water causes disinfection. 100 degrees centigrade for 30 minutes destroys non-spore forming pathogens. Again, non-spore forming. Spores are the heartworm that kills endospores. So boiling water, 30 minutes, destroys non-spore pathogens. Pasteurization. Heat's applied to kill potential agents of infection and spoilage without destroying the food flavor value. It's a flash method, 771.6 degrees centigrade for 15 seconds. It's not sterilization. It kills non-spore forming pathogens and lowers overall microbe count. Does not kill endospores or many non-pathogenic microbes. So a lot of the microbes that don't cause disease aren't killed by it, and it doesn't really matter because they're not going to cause us any problems. Ultra pasteurized, which is sterilized, is produced. And that's 134 degrees centigrade for 2 to 5 seconds. It's a lot higher temperature, almost double. This is what a small flash pasteurizer looks like for dairies, for cow's milk. Dry heat uses high temperatures and moist heat. Incineration, flame, electrical heating coil, infrared incinerators. Ignites and reduce microbes and other substances. Very common practice in microbiology labs, like have incinerators. Hot air, dry ovens, heat is circulated air, 150, 100 degrees centigrade, 12 minutes to 4 hours, depending on what you're trying to get rid of. And it coagulates the proteins, it sticks them together, makes them non-effective. This is an incinerator on the tip once you're dipping in different microbes, and you have a splash screen around to help protect it from splattering. That's an incinerator. And again, the forms of heat, equipment, and what they cover. So you have steam under pressure, unpressurized steam. You have pasteurization, where you have flash pasteurization, or you have ultra high pasteurization for sterilization. Boiling water, 100 degrees centigrade for 30 minutes. Does not kill endospores. Dry oven. Incineration is a flame that actually burns it. And then cold and desiccation. Desiccation is drying it out. So microbiostatic slows the growth of microbes. When you put some in the refrigerator, why do you do that? You slow the growth of microbes down. Refrigeration is 0 to 50 degrees centigrade. Freezing it is less than 0 degrees centigrade. It preserves food and cultures in microbiology. Desiccation, dried out. We gradually remove water from cells, leading to metabolic inhibition. It stops metabolic processes from occurring. It's not an effective microbial control. Many cells will tell the ability to grow when water is reintroduced. So you dry them out, you add water into it, and they grow again. So it's not very effective at reducing your microbial control. Lyophilization is freeze drying to preserve something. So which of the following compounds is microbial effects? Boiling, pasteurization, incineration, freezing, and desiccation. Okay, so which one's going to kill microbial effects? Boiling, yeah, 100 degrees centigrade, 30 minutes, yep. Pasteurization, yeah, because microbial effects. So not kill endospores. Incineration, definitely. Freezing, no, because if you freeze it, you can rethaw back out. Desiccation, take away the water. Freezing just slows it down. Desiccation stops it, but it'll come right back if you add more water to it. So if which one comes microbial effects, it would be those three, A, B, and C. Okay, boiling, pasteurization, and incineration. Methods to control microbial growth. One way to control it is with radiation. Radiation is energy emitted for atomic activities. Dispersed at high velocity through matter or space. So it's an X-ray beam. It's just a high energy ray, basically. There's two types of radiation that we use for microbial control. There's ionizing radiation and there's non-ionizing radiation. Your ionization is your very high energy radiation, your gamma rays, your X-rays, your cathode rays. Non-ionizing is like ultraviolet radiation, sunlight. Right? This is the different types of light that there is. We got from very low energy, high wavelength, very long wavelengths here. Okay, your radio waves, microwaves, infrared, visible, ultraviolet. There's your UV, there's your X-ray, and there's your gamma rays. Very high energy rays as you get towards gamma rays. Okay. So ionizing radiation is penetrating radiation. It penetrates deep, causes electrons to leave their orbit. Remember, if you remember, the nucleus of the atom has the protons and neutrons inside of it, and these electrons spin around it in different, what's called orbits around the nucleus. The energy that comes in, gamma radiation, hits these electrons and causes them to jump out of their orbits, move into different orbits. Okay, so it actually causes electrons to leave the orbits with the energy being hit by a gamma ray. Okay? Gamma rays, X-ray, cathode rays, all those are ionizing radiation that's caused that electrons, what's called being in their excited state. They leave their ground state. Okay? And this is what happens, it breaks the DNA inside the cell. So that's the damage that it does with radiation, that's what it affects. Non-ionizing radiation has very little penetrating power. Okay? It creates what's called pyrimidine dimers, which are links that break use like adenine and thymine to go together. It breaks that bond between them and causes them to link to adjacent nucleotides that are similar. I'll show you a picture of that in just a second too. And it interferes with the replication of DNA. So two different ways for radiation to work. This is your ionizing radiation. Comes in here and hits the electrons, hits electrons from the cells, causes them to be excited, leave their orbit. So it hits the DNA and causes the DNA here to fracture. So it breaks the DNA. That's ionizing radiations, gamma rays, cathode rays, and X-rays. Non-ionizing radiation comes in here and it hits, and you see right in this region here, it causes the bond, the hydrogen bonds between the nucleotides to break apart, and then it links these two adjacent nucleotides together. Right in there. Okay, those are called dimers. Okay. Well, here's a good example of a dimer right here. This is your normal DNA where it pairs. Adenine pairs with thymine, guanine pairs with cytosine. Then you got UV radiation. You go, it's called a thymine dimer, where thymines next to each other right here, and it breaks that bond and establishes a new link right here between the thymines. So it breaks the adenine thymine bond and has the thymines linked together. Okay, that's what's called a dimer, a pyrimidine dimer. You can see right here the bond point between the two thymines. Okay. Application we do with radiation control. These are raspberries that have been exposed to radiation 5 days later. These are raspberries that have not been exposed. Okay, not treated radiation 5 days later. And you see the different microbial growth. So the radiation has killed the microbes so they don't multiply and grow into these colonies. Okay. Oh, how we control is these different containers here. We'll show you how those work. So this is our summary. We have ionized radiation, is sporicidal and penetrating. It kills spores and it penetrates deep. Okay, that's ionized radiation. Cobalt radiation gives off gamma rays, X-rays, and cathode rays. They fragment the DNA. They break the DNA apart. Okay, highly mutagenic, cause mutations by breaking the DNA. Okay, medical uses is cold sterilization of packaged products and medical supplies, instruments, sterilization of foods, okay, sterilization of drugs and vaccines. It's rapid and penetrating, prevents infection and spoilage. Okay. Non-ionizing, like ultraviolet radiation, sporicidal, okay, and non-penetrating. So it still kills the spore, but it does not penetrate. Okay. Germicidal lamps or generators deliver UV lights, creates abnormal bonds between adjacent thymines and cysteines, and produce what's called your pyrimidine dimers. Okay. Produces deletion mutations because it causes that one place, that link is now broken that bond, so it's not part of when it reads across from messenger RNA. So it can cause a deletion mutation on the DNA. Okay, mostly disinfection of air for some liquids, few solids. Reduces airborne pathogens in medical and dental offices, hospital rooms, and operating rooms. It's commercially used for clean rooms and food processing areas. Works on liquids like water, milk, drugs, vaccines. It exposes UV in thin layers. Because remember, it's not penetrating. So it only exposes the top layer. Solid materials like room surfaces, food, tissue grafts, drugs, and instruments. Okay, the lack of penetration through solids limits its application. Okay, it's not penetrating like the ionized radiation is. Okay, direct exposure can be dangerous to your eyes and your skin. Again, the tanning booths, you wear protection over your eyes, help protect them from the UV radiation, and this skin cancer can develop from too much exposure to UV radiation. Okay, this is a pallet of apples being irradiated with cobalt-60. Cobalt-60 is radioactive and emits gamma rays. So that's ionizing radiation being treated for apples. Same with a toothbrush. You get these UV ultraviolet rays, and it disinfects your toothbrush. That's more of a gimmick than anything else. It doesn't do any good really with a toothbrush. When you replace your toothbrushes, I mean, you should replace the toothbrush every 3 to 4 weeks. Okay, after that, you just brush it with bacteria because it just gets into the bristles. Filtration. You can see you have the cell membrane, the filter acts here. Liquids can go through the pores here, but the other materials and microbes and everything cannot go through. Okay? So you can use filtration to decrease the microbial count. So filtration is a physical removal of microbes. Okay, it's just a layer by passing a gas or liquid through the filter. We use it to sterilize heat-sensitive liquids and airs in hospitals, isolated and industrial clean rooms. So use a filter, the microbes can't pass through the filter, it cleans the air or cleans the liquid. Okay. We talked about disinfectants, antiseptics, sterilants, degermers, and preservatives. Okay, some of the qualities you want in a germicide, something that kills germs. You want rapid action in low concentration, because you don't make high concentration, it could cause damaging effects to the people using it. You want it soluble in water or alcohol, so it can be applied, and you want it to be stable. You want it to be broad spectrum, kill a bunch of bacteria, not just a very specific one, but several, and very low toxicity to the person, to the people around the area. You want it to be penetrating, so it penetrate multiple layers. You want it to be non-corrosive and non-staining. You don't want to damage the materials that you're sterilizing or disinfecting. You want it to be affordable and you have high-level germicides, intermediate-level germicides, and low-level germicides. Okay? High-level germicides kill endospores. Remember, endospores are the most difficult to kill. We can use those as sterilization, to sterilize instruments, sterilants. Devices that are not heat sterilizable and tend to be used in a sterile environment in the body tissues. Okay? Intermediate level kills fungal spores, but not endospores. Okay? So tuberculous bacillus and viruses, this disinfects devices. Okay? So use that for come with your mucous membranes, but are not invasive in the body's mucous membranes. Low level eliminates only vegetative bacteria, bacteria on your skin, outer areas, vegetative fungal cells, and some viruses. It cleans the surfaces that touch the skin, but not the mucous membranes. So different levels of decontamination is needed. Okay, high-level germicides can sterilize. Intermediate level germicides can disinfect. Low-level germicides can just eliminate the vegetative bacteria, so touching the skin but not the mucous membranes. Okay. Factors that affect is the nature of the material that's being treated. Okay, it's the degree of contamination. Okay, the time of exposure required. We talked about a little bit last time, how much time is required, whether the what the temperature is at determines the time of exposure to create the desired effect. The concentration of the chemical agent, how strong it is, the strength and chemical action of the germicide. It's expressed in dilution factor as usually ppm, which is parts per million, which is a percentage of how many do it. It's how many parts there are per million of the solvent. Okay. So these are the different qualities, different agents that we use over each of these two. We can use chlorine, iodine, phenolics, and chlorhexidine. Chlorine is a sporicidal, kills spores, but it kills them very slowly. Iodine is a sporicidal, kills very slowly. Phenolics kills some bacteria, viruses, and fungi. Chlorhexidine, mostly bacteria with some viruses and fungi. Okay. Alcohols, we talked about that before, mostly bacteria, viruses, and fungi. Hydrogen peroxide is sporicidal. It kills spores. Okay. Quaternary ammonia compounds, bacteria, virucidal, and fungicidal activity. Soaps are certain very sensitive species to soaps. Okay. Mercurials are very weak microbiostatic. Okay. Mercurials are very toxic if ingested or inhaled or absorbed, though, too. Mercury is very toxic to the human body. The advantage of soaps, though it's very low, is it's non-toxic. Very few of any toxic effects. Okay. Silver nitrate is bactericidal. It will kill bacteria. Okay. Glutaraldehyde is sporicidal. It's a high sterilant. Orthophenylaldehyde is sporicidal. It takes time to do it, though. Okay. Ethylene oxide gas is also sporicidal. It's also sterilant. And different types of dyes are weakly bactericidal and fungal. Okay. So these chemicals approach the idea by having many of the following characteristics. They're broad spectrum. That's what you want. You want low toxicity to the host. You want fast action. You want penetrating. Okay. Residual effects should be minimal. You want it to be stable and potency in organic material. And it has to be soluble usually in water or alcohols. All right, so these are different categories of germs that we're going to talk about. We have the halogens, which is your chlorine, bromine, fluorine, and iodine.
you ever have a swimming pool or a spa, use chlorine and bromide to keep your waters at that at good levels where it's healthy. We're not they're not full of pathogens. The phenolics, chlorhexidine, alcohols, hydrogen peroxide, aldehydes, gases, detergents and soaps, heavy metals, dyes, and acid alkyls. Okay. So the halogens is us chlorine and bromine are the two big ones. Okay. We're using germicide preparations. Chlorines is your hypochlorite, which is bleach. Okay. And chloramines. We denature the disulfide bond. When proteins are held together, there's the primary, secondary, tertiary, and then quaternary structure of proteins. Okay. With the tertiary, the protein does not become active until the tertiary layer, where everything bonds together. And it's how it goes by hydrogen bonds, disulfide bonds, and hydrophobic and hydrophilic areas. Disulfide bond is just on a protein, you will have a sulfur bonded to another sulfur. Okay, that's a disulfide bond. Okay, and it breaks this disulfide bond, that changes the shape of the protein and becomes non-functional. That's what it comes by denatures it. Okay, so chlorine's an intermediate level. It's unstable in sunlight, and it's inactivated by organic matter. We use it for water and sewage, wastewater treatment plants. Okay, so it's inactivated by organic matter. So chlorine is what we use in swimming pools. Right? That's why in the heat of the summer, chlorine doesn't last as long. Okay, we put in the pool, have to do it over because the sunlight breaks it down. You ever been to a swimming pool where they tell you to take a shower before you enter the water? Because the organic material from your skin, okay, that you had sweat and everything else, that deactivates the chlorine in the pool. That's to have you rinse it off before entering the pool. So when chlorine is unstable in sunlight and inactivated also by organic matter. Iodine. Iodine is another one of the halogens. Okay, that is a iodophore, and this is in betadine solution when you do your scrubs for your surgery patients. Again, it interferes with the disulfide bonds of proteins, breaks the changes the shape of the protein, makes it inactive. It's an intermediate level, and it's a milder medical and dental degerming agent. It's a disinfectant, and it's an ointment. Okay. So chlorine gas, disinfections of drinking water, sewage plants, hypochlorite like bleach, used in fumitows. This is for swimming pools, spas, drinking water, wound asepsis, cleaning up wounds, and stain removal. Chloramines, it's similar to chlorine, in treating water supplies, but also used as sanitizers and a disinfectant, and for treating wounds and skin surfaces. Iodophores, those are the betadine or iodine compounds. Yeah. Mostly common iodine for skin and mucous membranes. Antiseptic for surgeries. In injections, cleans the area so you don't get bacteria in the area. Surgical hand scrub, disinfect equipment and surfaces. Okay. I'll prevent eye infections in newborns. Okay. Those are your iodophores. Elemental iodine. Okay, top anesthetic prior to surgery. Sometimes for Vernigen is a medium level disinfectant for our plastic instruments. Don't have to use heat. Clean thermometers with it. Okay. All right. This is a slide of a cantaloupes. They're being done with chlorine water. This kills the salmonella bacteria that are on the surface of them before they're being shipped out. So we use this chlorine to kill the salmonella on the surface of the cantaloupes before they're being shipped. Okay. Prominent iodine solutions, betadine, these are for surgeries on patients. Okay. Phenols an acrid poisonous compound. Okay. Phenols is a benzene ring. When you talk about benzene in chemistry, benzene is a 6-membered carbon ring with alternating double bonds. That's what it looks like. And then it has one edge with a OH group or alcohol group. Okay. That's a phenol. Okay. These are used in a lot of cleaning products. They are toxic. Benzene also used to be used. Benzene is just the ring by itself. Back in the 1960s, we used to use that as a cleaning product, disinfect hospitals. And then we found out that a lot of the janitors were dying of liver cancers. And it's because we found out this benzene here, when inhaled airborne, just breathing the fumes of benzene causes liver cancer. So it's not used anymore. It's now used phenols. It's a little more stable, but it is still toxic. Okay.
So it has to be handled very carefully. Okay? And what it does, it disrupts the cell walls in membranes and precipitates proteins. So it puts in the proteins of those cells wall and opens those cells wall up and causes them to leak. It's a low to intermediate level. It's a bactericidal and a fungicidal and a virucidal, but does not kill the spores. It kills your bacteria, your fungus, and your viruses, but does not kill the spores. Lysol, triclosan, or antibacterial additives to soap, which use phenol. Toxicity of phenolics make them questionable choice for antiseptic. You know, they are still toxic, not as toxic as benzene, but they're still toxic. Again, here's your phenol. And in organic chemistry, you have phenol, and then there's if you have a OH group and a CH3 group, it's called creosol. And then you have 3 positions where it could be on the ring. It could be at this position here, this position here, or this position here. So this is 1, this is 2, this is 3. The other position is just the mirror image, you flip it around. So if it's at number 1, it's called what's called ortho, which is an O. If it's in the number 2 position, it's called meta, which is an M. At the number 3 position, it's called para, which is a P. So this is the P creosol, the CH3 at the para position. O creosol is at the ortho position. You'll see those and identify different compounds if you're looking at them in a medical journal, something like that. Okay. And you see chlorphene and hexachlorophene. Again, you have the OH group, the phenol group here with the benzene ring, which gives it its cleaning power. Okay. So chlorhexidine. Chlorhexidine is a surface and protein denaturant for denatured proteins with a very broad microbial properties. Right, so it kills a wide range of bacteria. Low to intermediate level, Hibiclens and Hibitane. It's used as a skin degerming agent. Okay. For pre-op scrubs, skin cleaning, and for burn patients. And these are the different forms of phenolphthalein and chlorhexidine. Creolin is a household version of phenol. Okay, used in floors, veterinary clinics use it. Bisphenols. Okay. It's used in the home and commercially available products. Hexachlorophene. Okay. Physohex for hospitals and home use to control outbreaks on skin infections. And triclosan. Okay. Antibacterial compound used to soaps, cosmetics, and many other household products. And then the Hibiclens, the chlorhexidine. It's an alcohol aqueous solution. It's commonly used for hand scrubbing. Okay, preparation of skin safe for surgical incisions, injections, and for patient cleanings. Okay, so which of the following is not true about hypochlorite? Kills by denaturing. It is light sensitive. It's often used for disinfecting water. It slows the release of iodine.
Is it D?
I would say you're right.
I'm just guessing. I don't know, because all the rest is true.
That's exactly right. That's the perfect way to do it. All the rest are true. It denatures proteins. It's very light sensitive, like talking about swimming pools. It's used to disinfect water in swimming pools. It does not have nothing to do with the release of iodine. So it'd be D, slows release of iodine. Because the other 3 we know are true. Alcohols. So only ethyl alcohol and isopropyl alcohol, okay, are suitable for microbial control. So only those 2 alcohols, ethyl and isopropyl. Concentrations of 50% and higher dissolve membrane lipids and coagulate proteins of the bacterial cells that are found in your skin. Vegetative bacterial cells. Okay, so you need concentrations of 50% and higher for either isopropyl or ethyl alcohol. Ethyl alcohol is drinking alcohol, we drink. Isopropyl is rubbing alcohol. Water is needed for proteins to coagulate. So alcohol shows a greater microbial activity at 70% concentrations than at 100%, because you need the water for the proteins to coagulate. If it's 100% alcohol, there's no water. It's 100% alcohol. And you need the water for the bacteria to stick together to clean the surfaces off. So 70% actually works better than 100% for reducing microbial contamination. That makes sense? Because you have 30% water, and water is needed for that coagulation of the bacteria. Okay. Alcohol gels we use in hospitals. Okay. Hydrogen peroxide. Hydrogen peroxide, very unique compound. Okay. It produces highly reactive hydroxyl-free radicals that damage protein and DNA while decomposing oxygen gas to toxic anaerobes. Anaerobes are bacteria that live without breathing oxygen. Okay. H2O2 is peroxide. It breaks down to water plus oxygen gas. So let's take example the mouth. Okay. The mouth, you have gums that support the teeth. So you have I'm not a great artist, but here's your tooth. Okay. Here's the gums that surround it. Okay. In between the tooth and the gums right here is a pocket. Okay. No oxygen gets in that pocket. So you have these anaerobes that live there that cause obstruction, and that's what causes periodontal disease, the breakdown of the support of the teeth. Okay. Now, if you rinse with hydrogen peroxide, hydrogen peroxide breaks down to water and oxygen. So if you rinse and swish, you're releasing oxygen into the crevices where the liquid is going. So you put oxygen into these pockets down here between the teeth and the gums. These are anaerobes. Okay. Oxygen is toxic to them, so it kills the bacteria that are causing the periodontal disease by producing oxygen. So if you need to treat anaerobes, a bacteria that live without the presence of oxygen, you produce oxygen, it kills the bacteria. So they're antiseptic, low concentrations. Strong solutions are also sporicidal, will kill spores. Okay. Disinfection of contact lenses. Okay. Bubbles producing, you see the bubbles being produced in here, all these little bubbles down there. That's all oxygen being released from the hydrogen peroxide. Okay, so application of alcohols and peroxides. Ethyl alcohol. Ethyl alcohol is what we drink. That's your vodka, your bourbon, your gin. That's all ethyl alcohol. Beer. All that you drink is ethyl alcohol. The only thing different is the percentages. If it's 5%, it's beer. Wines vary from 3 to 12%. Bourbons go up to 40, 50%. I mean, the higher the drink, sometimes the more alcohol content there is. So ethyl alcohol is a skin degerming agent. Okay. Surface action removes skin, oil, soils, and some microbes, sheltering the deep layer of skin. It's occasionally used to disinfect electrodes and face masks. Isopropyl alcohol. Isopropyl alcohol is rubbing alcohol. Some disinfection of objects, surfaces, limited skin cleansing of that one. Okay, alkylated protein DNA, glutaraldehyde. These are your aldehydes. Glutaraldehyde in a 2% solution is called Sidex. Okay, it's a high-level disinfectant. It's used as a sterilant for heat-sensitive instruments. Remember, we sterilize things by heat and pressure. Now, if what we're using is sensitive to heat, we can't use that to sterilize it. We can use glutaraldehyde. You just put in there for 24 hours or longer. We'll sterilize heat-sensitive. You have to go in the mouth or into the human body. Formaldehyde, it's formalin. 30% aqueous solution. It's an intermediate to high level. It's a disinfectant, preservative, and toxicity limits its use. So it's very toxic. We use it as preservative in the morgues for when we embalm a person. Getting ready for it, we use a formaldehyde. Okay. So I think that is kind of easy ice cream. Technicians treat surgical instruments with glutaraldehyde prior to heat sterilization. Now, if you look at the picture, that looks like a squid. I don't think the picture matches the title on this one. I'm not quite sure. I think they got something backwards, but that's definitely a squid. Now you use glutaraldehyde to preserve specimens also. Okay, but that's not a surgical instrument. That's the squid. Gases and aerosols, strong alkylating agents, ethylene oxide, ETO, propylene oxide, PO, and chlorine dioxide. It's a high level, and it sterilizes and disinfects plastics and prepackaged devices and foods. And how we use it as a chamber, we seal it. We have air coming into that. We use a vacuum pump to force it out once it's done. And we mix the ETO cylinder here, and then a CO2 cylinder there to mix into the chamber and expose the
packaging material to that gas. We use it to, and these are the package items that we used, and it sterilized in the ethylene oxide sterilizer. Okay, so glutaraldehyde, we talked about. We use that for things that are damaged by heat. Respiratory therapy equipment, hemostats, fiber optic endoscopes, things you can't heat up. Okay. Orthophenolate, OPA, is a high level disinfectant uses and effects of glutaraldehyde. ETO, ethylene oxide. Okay. Heat sensitive plastics and delicate instruments used in the hospitals. Prepackaged medical supplies we use. Petri dishes. We use it for disinfect foods, spices, dried fruits, and drugs. Propylene oxide, PO. Okay. Sterilization of foods, nuts, powders, starches, and spices. Chlorine dioxide. Okay, is an air and surface sterilant. Treatment of water, food processing equipment, medical waste, decontamination of whole rooms, and space probes. Detergents. We use, these are quaternary ammonia compounds. Quaternary means 4. It's quats. Okay. It means there's 4 attachments to the nitrogen atom. That's ammonia. So it's a quaternary ammonia. Active surfaces of surfactants that offer membrane permeability to some bacteria and fungi, very low level. Remember, surfactant is a coating material that allows the surface of membranes to change. So it alters their membrane permeability. Okay, the body produces surfactant also. When you have a premature baby, a preemie's born, okay? A lot of times what determines if they'll try to save it or not is if they're at an age where they're producing surfactant. Because in the womb, the fetus does not breathe for itself. It's getting all its oxygen from the mother's breathing, being carried by O2, the hemoglobin in the mother's blood cells, crosses the placenta into the baby's circulation, and the baby uses the oxygen the mother's breathing. So the lungs do not function. In fact, we have a whole complete bypass system in the fetus, so lungs they won't use lungs at all. Okay, blood doesn't even go to the lungs because they're non-functional. Okay? When the baby's born, the lungs open up, okay, air comes in, the baby can breathe. Now, think of a balloon. Okay, when you first try to blow up a flattened balloon, it takes a lot of force, right? Once the balloon goes up a little bit, then it's easier to blow and expand. That's like your lungs. When the baby's lungs, infant lungs are born, they're completely flat. That initial force, it takes a lot to get a baby to breathe. Once they're expanded, the surfactant coats the lungs. Surfactant changes the surface and doesn't allow the lung to collapse when the air is expelled. So the baby breathes in and then breathes out, but the lungs don't collapse again. They stay inflated in and out and allow the baby to breathe. Now think about if the surfactant wasn't there. Baby does all that force, opens the lungs, breathes out air, those lungs collapse. You gotta do that same force again. Force those lungs open, and the lungs collapse. The baby's not gonna survive. And the problem is, even with a respirator, with a machine that does it for it, we have to force so much air into the newborn baby's lungs, we blow out their lungs. Because you gotta force them to open up every time. So surfactant is one of the key requirements, okay, of the age of when we determine if a premature baby is viable, to keep those lungs from closing. And that's what surfactant is. Surfactants coat a surface and they change and alter the membranes so they act differently. Okay, then in this case, we're using it for a detergent. In the case of the lungs, you're using it so the lungs don't stick together. It doesn't allow them to collapse. So soaps and alkaline compounds, like with laundry, things like that. Which microbicide destroys only highly sensitive forms, gonorrhea, meningitis, and syphilis are examples. So non-germicidal soap, you apply it, you rub it off, the microbe goes down, then it goes back up again because you didn't kill them. You apply it again, it goes back down. With germicidal soap, it means you're killing the germs each time. So every application, it starts to decrease the microbial count. So quats, quaternary ammonia compounds. Okay, disinfect, sanitize floors, equipment, services, and restrooms. Sanitizing restaurant utensils, food processing equipment. Okay, common preserving ophthalmic solutions and cosmetics. Soaps. Cleaning agents, sanitizers, industry in the home. Preparing instruments for heat sterilization. The majority of stuff off first. Degerming patient's skin, hand washing, preoperative hand scrubbing. Okay. Proper hand washing with soap is one of the most important control methods for healthcare and personal hygiene. How many times did they, with COVID, it reminds you, wash your hands? That's our first step. This is what we're talking about. This is a quaternary ammonium compound, quats. I mean, there's 4 things attached to this nitrogen atom. Ammonium is nitrogen with 4 attachments. Quaternary means 4. This is benzoyl chloride. It's a salt used in our detergents and soaps. Soap is for hand washing. Okay. Which of the following kills by producing oxygen radicals? What produces oxygen that will kill anaerobes? Would it be alcohol, hydrogen peroxide, aldehydes, gases, or soap? Which one of those produce oxygen?
Peroxide.
Peroxide, you got it. Hydrogen peroxide. Hydrogen peroxide breaks.
Wi-Fi isn't set up. You can find instructions in the help section of your Alexa app.
You everybody hear that?
Yeah.
I don't know what that was. I don't know if that was mine or something, but I don't know. But Wi-Fi is going pretty good. Hydrogen peroxide breaks down to water and oxygen. And that's what kills anaerobic bacteria. It is hydrogen peroxide. That will be on your nursing exams too. That's on your in-class test. And that's when you should remember. Heavy metal poisoning. Okay. Solutions of silver or mercury kill vegetative cells with low concentration by inactivating proteins. They inactivate proteins, inactivate enzymes in your body. Oligodynamic action, they have antimicrobial effects in exceedingly small amounts. You don't want them in large amounts. Large amounts they call toxic effects. Heavy metal poisoning is very, very dangerous. Silver nitrate, methylate, and silver. Okay. You can see the metal that's around it. You can see the sterile zone where the metal is deposited has an antimicrobial effect. It kills the microbes around that area where the heavy metal is. Organic mercury. Okay. It's a weak antiseptic. Can be preserved in cosmetics and ophthalmic solution. It used to be used in the flu vaccine. They used to use mercury as a preservative. That is not done anymore. There were too many. I don't know. I don't think there was scientists backing it up, but a lot of people claimed it caused autism. I don't think that's ever been proven, but mercury used to be used as a preservative in some of our flu vaccines. Silver is sulfadiazine ointment. Okay, we use it for dressings. Prevents infection in 2nd and 3rd degree burn patients. Silver nitrate, topical germicide for mouth ulcers. Okay, it kills the herpetic lesion. It kills the canker sores. And occasionally put it inside a root canals to kill tissues down deep inside the tooth. Metallic silver is in catheters to prevent urinary tract infections in hospitals. That's added to paint, plastic, steel, way to control microbials. Okay, survival items like toilet seats, stethoscopes, and walls and floors in the home. Colloidal silver, okay, it's mild germicide, ointment for rinses for the mouth, nose, eyes, and vagina. Okay. Aniline dyes, aniline as a nitrogen compound containing dyes are active against gram-positive species of bacteria and various fungi. Used sometimes for antisepsis and in wound treatment. It's very low level, has a narrow spectrum of activity, so it's not used much. You want things that are a broad spectrum. It says a narrow spectrum of what it can kill. Acids and alkyls, it's organic acid prevents spore germination and bacterial and fungal growth. Acetic acid inhibits bacterial growth. Propanoic acid retards mold. Lactic acid prevents anaerobic bacterial growth. We produce that in the body when our muscles have been overused and go into anaerobic respiration. Benzoic acid and sorbic acid inhibit yeast. So here's the different ones, a particular agent and what they are. It's just a summary of it here.